today's experiment, of course, is based, of course, on density. And as you recall, right, in class, we noted what? That density is oftentimes referred to, of course, as a derived unit, right? Density, of course, enables oftentimes, of course, as chemists to determine, of course, some unknown, of course, substance. And so actually, believe it or not, in today's experiment, we're going to be using density, right? So one thing we're going to be doing is use density to determine, of course, right, this unknown, of course, cylindrical block. And so, please note, density being a derived unit, it's derived from what? It's derived, of course, from the units of mass, right, and volume. So oftentimes we note that density is just equivalent, of course, what? To the mass per unit volume. Now, you might say, therefore, what exactly, right, are the units of density? Well, it's mass over volume, and so, of course, the mass determined, of course, by means of a balance is going to be reported in grams, and that volume, of course, is either reported what? In either milliliters or centimeters cubed. Now, you might also say, when is that volume, of course, reported in centimeters cubed? So please note, whenever you have a regular, so if we have a regular shaped object, that means, of course, what? It could be a cubic block, for example. Then under those circumstances, of course, the volume is determined by means of its dimensions. And so if I had a cubic block, for example, right, I could determine what the volume by measuring what? The length, the width, and the height. If it's a cube, of course, all sides, of course, would be equal. But it doesn't have to be, of course, a cubic block. It could be, of course, what? Any regular shaped object. And so in this lab, you're actually going to determine what? The goal, of course, will be to determine the density of a cylindrical block. And so you should note, for that volume, right, there's an equation that states what? That the volume of this object, no matter what size, is going to be equivalent to what? Pi r squared, right, times h. Now the challenge is, what exactly is r? So please note, r, honestly, is just what? A half of the diameter. So during the experiment, I'm going to be giving you, of course, the diameter, of course, of this cylindrical block. And h, of course, is the height, of course, right, of this block. And so, r squared, so centimeter times centimeter, right, centimeter squared, times, of course, the height also in centimeters, will give me that volume, of course, right, in, of course, cubic centimeters. Now, likewise, of course, that volume is oftentimes reported in milliliters. When is that volume, of course, in milliliters? Well, please note, here, of course, right, the object is usually what? An irregular shaped object, but it could also be a regular shaped object. But imagine, therefore, that I gave you my set of keys. You could also find the density. Well, readily you can determine, of course, what? The mass in grams, but how will we determine the volume? Well, that volume, please note, is determined by a method known as the displacement method. And so what do we do under these circumstances? Well, we obtain, of course, what? A graduated cylinder. That graduated cylinder, of course, right, is then filled with water, not, of course, to the max, but let's say we have filled that with water. We note, so here's some terms you're going to hear me talk about today. We note the initial volume, of course, of water in, of course, a graduated cylinder, and then we slowly add the object. What do you think is going to happen? Well, that volume, of course, is what? It's going to increase, and therefore, that displaced volume is exactly equal to what? That is actually equal to the volume, right, of our object. But because I'm reporting this, of course, in that graduated cylinder, you should note what? You should know that that volume now will be recorded in milliliters. Okay, now a few things I also need for you to take note of. There are a few vocabulary words. I'm going to go ahead and erase this for now. And so there are some vocabulary words that I need for you to be familiar with as we go through, of course, this experiment. And so as we proceed, my goal, hopefully, is that you should be able to predict which method, whether it's the displacement method or, of course, using dimensions, which method is the most accurate. So what do I mean by that? And so when we talk about accuracy, of course, in chemistry, or actually any science course, the goal is how close, of course, are your measured values. So your goal here is to determine how close are your measured, of course, value, right, to, of course, what I'm going to call what? That actual value or the theoretical value. And so, I need for you to report as you write up this lab report. Is it, of course, the displacement method? Or is it, of course, what? The method using dimensions, right, that was the most accurate. Likewise, of course, precision. I need for you to determine which method was more precise. What exactly do I mean by that? And so, in this case, it just really matters what? So how close, or of course a series, right, of measured values to each other. So, was your data fairly random? Or, of course, were the values that you obtained, because I'm going to repeat this experiment 3 times, or the values, of course, that you obtained very close to each other? So that's 2. The next step, of course, is that we're going to be looking at what? At different properties. So in class I mentioned, of course, what? That properties could either be what? Physical, right, or chemical properties. But for now, I'm going to focus primarily on whether that property is extensive or, of course, what? Intensive. So what exactly do I mean by these terms? So please, again, recognize this fact. Imagine, therefore, that I have a graduated cylinder with water. Do you agree that the mass of water in that container depends exactly, right, on the amount of water that I've added? And therefore, that property, the mass of water, is therefore said to be what? An extensive property. Likewise, if I added, of course, water to that container, the volume of that water will also depend, do you agree, on how much, of course, water I added to my sample. And so therefore, again, mass and volume, not just mass, but mass and volume are oftentimes in chemistry referred to, of course, as extensive property. The amount depends, of course, of the value, I should say, depends, of course, on the amount that was added. However, if I took that same container of water, and if I place that in the, of course, the freezer, do you guys agree? That, of course, what? That is going to freeze at a specific temperature. Whether I have 10 mLs of water or 100 mLs of water, I can assure you, of course, right, that that property, right, will be exactly the same. So the freezing point, but not just the freezing point, or the boiling point of water is exactly the same no matter how much water I have in that container. So here's my goal. So my goal, or your goal in this experiment, is to determine what? Is density, so now don't forget, now we're focusing on density. Is density an extensive property? Or do you believe, right, that density, of course, is an intensive property? And that you should be able to conclude, right, at the end of this, of course, section. And again, just to make sure that you understand exactly what's going to happen, you're going to be given what? 3 cylindrical blocks. Notice, of course, right, they have different size. So do you think, of course, that it matters? Will the density change? Depend, of course, on the size or not. And then finally, this will do something that hopefully will be a bit, at least in my opinion, a little bit of fun, right? We're going to try to determine the density of an egg. So I'm going to go ahead again and erase this from the board. And so part 2 of this experiment, still using the principles, of course, of density, will be to determine the density, right, of course, an egg. But guess what? This egg, right, there's one that's been sitting for about 2 or 3 weeks in someone's refrigerator, and one, of course, is one that was recently purchased. And so I'm going to be looking, of course, at both the density of an old egg and the density, of course, of what we call what? One, of course, that is fairly new, was recently purchased. Do you think that they're going to have the same density? If not, why not? So that will be the challenge. Now, how, of course, are we going to determine, of course, the density? Well, please note, we're going to be using, of what? We're going to be using the principles that you should realize what? That the density of the egg will be exactly equivalent, of course, right, to the density of a salt water solution. But under what conditions? when, of course, that egg, right, floats. So I'm going to be adding, of course, salt, of course, to water. And when, of course, that egg floats, I can guarantee you, then, of course, what? Then the density of that egg is exactly equal to the density, of course, of that salt water solution. Now, whether, of course, the old or the new egg, of course, has a lower density, I'll wait for you to determine that from your data. But then, of course, the big challenge will be why. So please note, as you try to answer that question, why, don't forget, right, that that shell consists of what? Calcium carbonate. And calcium carbonate, of course, will allow water to, of course, what? To leave, of course, right, to evaporate, and that's it from that egg. All right, so we're going to be moving on to the wonderful experiment. So we'll be back in 5 seconds. Alrighty, so in part 1 of this experiment, you're provided, of course, with your cylindrical blocks. You're also provided, of course, with a balance to record the mass. And then, of course, these are graduated cylinders. I have actually pre-measured 35 mLs, of course, of water in each of these containers. So you'll need, of course, your graduated cylinders in order, of course, to determine, of course, the volume using displacement method. So we're going to spend some time now going over to our balances to record the mass, of course, of each of our cylinders. And after recording, of course, that mass, we'll come back, of course, and determine, of course, the dimensions of each of these, right, using, of course, our ruler. So let's move over to our balances. So when we're in the laboratory, it is extremely important that we do not add objects directly to our balances, despite the fact, of course, that these are even non-toxic. These are not, of course, chemicals. We still make sure, of course, that our objects, of course, are weighed either on a weighing paper. This is of course, as a weighing boat, okay? And so the first thing we do, of course, in the laboratory is that we open, of course, we just slide, of course, this little door, right? Close. You want to make sure that you close between each, of course, of your readings. And then oftentimes what we do, of course, in the lab is that we do something that's called tearing. Literally, that just involves, of course, setting, of course, right, our balance back to 0. And so you'll notice, of course, that right now, therefore, whatever object I add to this container, right, will just be the mass of that object. So I'm going to start off, of course, with my smallest cylindrical block. That's block number 1. And then I'll move on to blocks 2 and 3. So I'll open, of course, my winter here, and I'll add that object. I'll close between each reading. And so right now, the mass, please note, of my first cylindrical block, block number 1, is actually 7.354 grams. Now you might say, why do I not go out to 4 decimal places? Oftentimes, of course, right, any air movement tends, of course, to change that last digit. So in our recordings, we oftentimes just go to 3 decimal places. I'm going to open again, check to make sure, right, that this goes back to 0 grams. If not, I will re-tear. So, oops, see what I mean by that beautiful wind? So any movement, of course, will change this. I'll give it another minute. Perfect. And so now it's back to 0, of course, grams. I'm adding, of course, object number 2. And then I record the new mass. And so that new mass, of course, is 12.020 grams. I'll allow it again to go back, of course, to our start at 0 grams. And then I'll add my third object. And now this new mass, right, for object number 3 is 16.692 grams. Okay. I'll move back over to our workstation to complete the other part of this experiment. So in this section, we're going to determine, of course, right, the dimensions, of course, of our objects. And I'm going to go ahead and start, of course, with cylindrical block number 1. Again, please note, I will be, of course, recording what? Both of the diameter as well, of course, as the height, right, of these blocks. And so using, of course, my centimeter ruler, I'm going to go ahead and look at the diameter. You might notice, of course, I might have a difficult time, of course, in seeing this directly. However, please recognize, of course, that I've already pre-recorded, of course, these values. And so the diameter, of course, of this block is 1.60 centimeters. Do not forget what we said, of course, in class, right? That this device measures, of course, to 2 decimal places. Likewise, I'm going to go ahead and determine, of course, the height of my block. And so for my cylindrical block number 1, this is the smallest block, it is 2.35 centimeters. And I'll repeat the same thing, of course, for blocks numbers 2 and 3. Now, you should expect, of course, right, that these cylindrical blocks, if you look at them, right, they have the same, in terms of diameter, they're the same diameter. And so again, that diameter is 1.60. And then the height of block number 2, height of cylindrical block number 2, please note, is actually 3.85 centimeters. And for number 3, just to make sure I convince you that the diameter is the same, again, the diameter is 1.60 centimeters. And that height of course is 5.30 centimeters. Now again, remember we know, of course, in class, if of course the height was 3.3 centimeters, if you thought it was exactly 3 centimeters, you will still need to note, of course, right, that it's 3.00, because that's, of course, right, the precision, of course, right, of that device or centimeter ruler. Okay, now with that in mind, you should now be able to determine what? Using, of course, the dimensions and, of course, the mass, you should be able to determine the density of this object solely by, right, its dimensions. Alright, so now I'm going to move on now, right, to the second part of this experiment. So here we're actually using a principle from physics, right, the Archimedes principle, right, which states, well, that the volume, of course, that is displaced by this object is exactly equal to the volume of that object. And so what I've already done is that I've added exactly 35.0 milliliters, of course, of water to each, of course, of my containers. These are called graduated cylinders. And so what you're going to notice I'm going to do is that I'm going to then walk slowly, making sure that I do not spill. I'm going to slowly add, of course, what? The objects, of course, to this container. And of course, what should happen? Of course, the volume hopefully should increase. And then I will report to you, of course, the new volume. So here we go. So here's my first cylinder. I'm adding, of course, to my beaker that has, what, 35 mLs of water. I promise you did not spill. Here's my second. And boy, I'm making sure this does not spill so we don't have to start over. I'm adding, of course, my second cylindrical block to, of course, the water. I'm just going to let it slide in because we're trying to avoid any spills. And then I'm going to do the same thing. I'm going to add, of course, what? My block number 3, right? Note, of course, I'm just being careful to avoid any splattering. So I'm going to hold this down as much as I can. Beautiful. And so you should notice, of course, the sizes were different. Do you guys agree? And so you would expect what? That volume, of course, that displaced volume should be greater. So now let's go ahead, of course, and look at the final volume. Please note, it's going to be very important, right, when you're in the laboratory, to make sure that you're looking, of course, at eye level. But also, do not forget that there is, of course, what? That little concave curve, referred to, of course, as that meniscus. And so it's extremely important that as I record this, right, that I'm actually sometimes the best thing to do is to actually use a piece of paper to make sure you can see this correctly. And I'm looking, of course, at the bottom. I must look at the bottom, right, of that meniscus. At eye level, I need to look, of course, at the bottom of that meniscus. And so for my tube number 1, please note, the volume here, of course, is actually 39.8 milliliters after the addition of that cylindrical block. Again, for my block number 2, after the addition of this block, you can still see that block in that container, That new volume, right, is now 42.9 milliliters. Again, making sure that you're looking at eye level, making sure also that you're looking at the bottom of that meniscus. And for, of course, the third cylindrical block, right, that volume, of course, is 46.2 milliliters. And so the masses did not change. And so using, of course, what? Using, of course, the mass of your cylindrical blocks, and now, of course, what? That displaced volume, you should now also be able, of course, to determine what? The density of these three objects, right? Using, of course, the displacement method. So the goal of this part of the experiment is to determine, of course, the density, right, of an egg that was purchased about 3 weeks ago. So we're going to refer to that as our old egg. And, of course, one that was purchased 2 days ago, our new egg. And so to do so, I'm going to, of course, what? I'm going to add, of course, the egg to my container. This is just water. This is a container of water. And, of course, when, of course, this egg, right, is just sitting somewhere in the middle, then it's just floating. And when I say float, it won't be on the surface. Before it hits the surface of that water, right, I'm going to note, of course, that at that point, the density of my salt solution is, of course, exactly equal to, right, the density, of course, of our egg. In addition to that, of course, I'm also going to be using, of course, a pipette, right? And, of course, a pipette bulb, I should say, and a pipette. Why? Because, of course, once, of course, I have determined, of course, the concentration of the solution at which, of course, this egg is, of course, right, just about to float, I'm going to have to record the density, right, of the solution. And so how will I proceed with that? Well, of course, you'll notice here that I have 2, of course, beakers. The masses, of course, have already been predetermined, right? And so what I'm going to do, of course, in both cases, I'm going to be obtaining 10 mLs of course, my salt water solution. And so if I know the mass of my solution, and if I have, of course, right, the volume, don't forget that the volume will be 10 mLs in each case, then I can determine, of course, the density. So let's proceed. So starting off, making sure that I do not break this egg, I'm going to slowly add my old egg to my container of water. If there's any splattering here, it won't be a big deal, because I'm only going to be removing, what, 10 mLs, of course, of water later, in order for me to record, of course, right, that density. Okay, and so I need to grab my stirring rod. So here's my stirring rod. And so I'm going to slowly start adding my salt. But I need to make sure, because right, you notice, of course, that when I initially place, of course, the egg in my water, it just sinks. Do you guys agree? And if it sinks, what does that mean? Is it more dense or is it less dense? You determine that. So make sure you make a note of that, right, in the report. As I add, of course, the salt to my container, I also want to make sure that my salt completely, of course, dissolves. And I have not pre-measured this, so I'm just going to keep on adding my beautiful NaCl to this container until this wonderful egg starts, of course, to float. So if you notice, of course, right, I kept on adding, of course, the salt until, of course, right, the egg is just freely floating below the surface, right, of course, the water. And so at this point, the density, of course, of our egg, this is our old egg, is exactly equal to, do you guys agree, right, to the density of my salt water solution. And so what I'm going to do now, because, of course, the densities are exactly the same, right, I'm going to go ahead using my pipette and my pipette bulb, right, I'm going to go ahead, of course, and actually obtain 10 mLs of this salt water solution. I'm going to transfer it to my pre-weighed container. So you notice I have 2 containers here. Container number 1 I'm going to be using, of course, for my old egg. Container number 2, right, for the new egg. Please note, yes, these, of course, beakers are exactly a 50 ml beaker, but I need for you to recognize, right, that you still need to determine the mass of each, because it's not universal, right? The mass, of course, of each of these containers are certainly different. And so please record, of course, in your report that the mass of beaker 1 is 28.680 grams. And of course, the mass of beaker 2, this was already pre-measured, is 29.229 grams. Alrighty, so now I'm going to, of course, I'm going to obtain 10 mLs, right? So I place my bulb directly, of course, in my solution. And please note, when I roll this bulb up, what's going to happen is it's going to create a vacuum. And of course, my solution will slowly rise. I want to make sure that I obtain exactly 10 mLs. And so again, I need to make sure that I'm looking at the bottom of my meniscus. Notice, of course, that this will accurately measure, of course, to 2 decimal places. And so when it says 0, right, that, of course, is going to be recording 10.00, of course, milliliters of my solution. So the volume of my solution is 10.00 milliliters. What I'm going to do next is making sure that that volume stays the same. So sometimes I just have to make sure that it stays exactly the same. And I'm going to be transferring this, right, directly into, of course, beautiful, nice. I'm going to be transferring that directly into, of course, my beaker. So I'm adding, of course, the 10 mLs of my solution to beaker number 1. Again, keep in mind, of course, that the volume in both cases, right, is 10 mLs. We don't blow into these, of course, devices. I just gently tap on the sides to make sure that I dispense all, of course, of my solution. And then I'm going to take this over, of course, to the balance. And in a minute, I will give you the mass, right, of the beaker plus my solution. Okay, so what I'm going to do now, moving on, of course, to the, or a new egg. I'm going to remove the old egg from the container without breaking it. That would just be hilarious. And of course, I'm going to add, of course, the egg that was purchased 2 days ago. And let's see what happens. I added too quickly. Wow. Notice, of course, right, that egg actually, right, did sink to the bottom. What does that indicate? Is that egg more dense or less dense, right, than, of course, that old egg? And that's a question that you will need to answer later. And so to now, again, go ahead and find the exact, of course, density of my new egg. What am I going to do? Again, I'm going to add salt, right? And I'm going to keep on adding salt, right? Until, of course, right, this actually floats below the surface, right, of my H2O. So here we go. I'm adding it as slowly as possible so that I don't have to go back and add and re-add water. I hope you're able to see me. I'm going to try and get my hands out of the way here. So I'm adding salt. The more salt I add, the more concentrated this solution is getting, right? And so you're going to notice, of course, that the more salt I add, I'll get to the point, hopefully again, where my new egg, right, will float. Or where it just floats below the surface of that water layer. Again, I need to make sure that this solution is completely homogeneous, right? So all the salt must dissolve in order for me to get a true, right, a true density of this solution. I think I'm hopefully almost there. Hopefully I didn't add too much. You'll find out. Won't be nice if I added too much. And what do you think happens if I add too much salt? So if I add too much salt, right, I promise you that this egg will float above that surface. But I can always recover, right, just by adding a little bit more water to dilute my solution. That would just mean that my solution is just a bit too concentrated. The more sugar that I add, you should recognize, right, it's the more dense, right, that solution will be. Oh, the more salt that I add. Guys, you know I'm hilarious. There's a sugar lab that I've eliminated. Alrighty, still not there as yet. So you know that there is certainly a difference, right, in the density, right, of my new egg versus, of course, that old egg. But I need for you to understand why. Why is that the case? I'm not going to give the answer. You can do a little bit of reading. But keep in mind it has to do with the fact that it does have a shell, right, made, of course, of calcium carbonate. I think I'm almost there. All I'm doing right now, each time when I pause, is I'm just adding, right, a small amount of salt. Hoping to get to that point where it just floats in the center of my solution. Okay, so now after adding, of course, the salt, additional salt, of course, to our original solution, you can now see, of course, right, that our new egg is not floating. So I'm going to repeat the same thing that I did earlier. I'm going to go ahead, I'm going to grab my beaker number 2, right? Remember I told you earlier that beaker number 2 has a mass of 29.229 grams. And so I'm going to do the same thing as I did before. I'm going to remove, right, don't forget, we're going to be using what, 10 mLs of our solution. So in both cases, right, the volume of my solution is 10 mLs. And so as I roll, of course, this barrel back and forth, what happens, of course, that's going to create a vacuum inside, of course, my tube. And that will allow me, of course, for that solution to rise slowly. Alrighty, again, making sure that you're looking at the bottom of that meniscus, right? So, okay, we have to look at the bottom of that meniscus. I will then transfer. I need to make sure it's exactly the same. And we're going to go ahead and transfer sorry, but I need to make sure it is just perfect. Okay, I'm going to go ahead and transfer, right, the 10 mLs of my solution. Again, we do not blow into the pipette. I just tap it against the side of this container to make sure, of course, that I've accurately dispensed my 10.00 milliliters. Again, I'm going to take this over to the balance. The mass that I obtain now is going to be, well, the mass of my container with the solution. So by differences, do you guys agree? You should be able to report the exact mass, right, of this solution. So the mass of beaker 1 plus the solution is 38.843 grams. That's the mass of beaker 1 and the solution. I'm going to do the same. I'm going to open, of course. I'm going to place my container with beaker number 2 and the solution. And the mass of beaker number 2 and that solution is 40.322 grams. And so using this information, by differences, you should be able to determine, right, the mass, of course, of solution 1, likewise the mass of solution number 2.